That is literally the point. I am a comedy genius.
You quit 18 across the street.
I definitely don't take advice from people less successful than me. Exactly. Don't understand. However, my intelligence is just on a different plane.
I don't understand what you're saying.
Exactly.
I'll go looking around.
I don't stare at me for about 5 minutes. Just go fast, you spin around.
Pretty fast.
Yeah.
She cried.
How close are we?
Well,
Yeah,
you're
you're
gonna
answer.
answer.
How
We
is
were like
this
going
funny?
to a bunch of parties.
3 more lessons.
5 weeks.
And so
Just a
I
national.
thought there was like a
What?
little
Just a
And
national.
I have to go like out and
Yeah.
so I was like.
Doesn't it feel like it's weird?
No.
No. It does not.
Doesn't it feel like we just got off the spring break last year and had the COVID lockdown?
No.
Not really. Do you feel like it's
So.
Feels like
I have the
this.
blue nails. for
What is
the
that?
outside.
Like
This past year.
Okay, like it did.
Like, do you feel like a different person at all?
I think
From
it
last
is
spring
like
break?
it.
I feel exactly the same.
I mean, I
That's
don't
a
do
weird
the
thing.
exact same
Oh,
thing.
I
Yeah,
don't know,
exactly.
I
You're
saw,
the
like,
same
saw
person.
my expression.
Yes. Actually, the same thing. That's all maybe.
That's true.
I know. Yes,
Yeah.
and no.
Anytime.
You just
Yeah.
call me.
Oh, yeah, thank you.
All the schools in trouble.
Yes, same, dude. What? My eyes are.
So you can't be at school.
Oh, really?
What?
You definitely
Because of
can.
allergies?
The pollen is kind of
Definitely-
stuck
definitely
everyone
great.
right now. Doesn't want
I wouldn't
to.
want to.
Dude, I should do. Bro, imagine being allergic to male. Higher male part, yeah. And not much pollen. I don't know, I'm pretty sure there's a lot.
All right, guys, we are almost done. We have 3 more lessons. So today, tomorrow, Wednesday will be our last lessons of the year. Thursday, we have the STAR test for freshmen and sophomores. So if you're not taking the STAR test, you will stay home. You don't even attend online classes. You may have assignments from teachers or whatever, but you won't have to check in or anything like that. Friday, we'll have a mat lab. Friday, problem set 13 is due. Tuesday, tomorrow, problem set 12 is due, which is from last week. Friday, problem set 13 will be due. Monday, we'll have a group bonus. Tuesday, problem set 14 will be due. Wednesday, we have our last test. And then we'll do some projects and we will be done. Yeah, I just said group bonus is on Monday. Yeah, so we'll do group bonus on Monday. Tuesday is review, Wednesday is the test. Okay, so as we've been seeing with our last few lessons, we're doing some kind of basic, very surface level application stuff with some of the matrices and things that we've been seeing. Today we're looking at computer graphics, which are obviously much more complex than anything we'll cover in 30 minutes of class. But we're going to kind of look at some basic ideas here. So we're basically taking 2 and 3 dimensional images, moving them around, transforming them through different things like translations, reflections, rotations, scaling, stuff like that. So translation is the main one that causes us a little bit of trouble because translations are not linear transformations. Right? If we shift everything, then when we translate the vector 0, we don't get the vector 0 anymore. It will also be shifted. So instead, we kind of think about if you want your image to translate, we actually kind of translate the axes instead to make it appear as though it's moving across. It'll also change the way we make our matrices so that our linear transformations like rotations and projections can interact with our non-linear ones like translations, and that we can kind of put those together and get more complex ones. The idea is these are all really simple. In general, a lot of these can be done very simply without a matrix. We come up with a matrix, put them together, and you'll get more complex transformations that cause other things to happen than a simple translation or a simple rotation or something. Okay, so we'll use matrices for this, obviously, just like we've been doing for most things this semester. Since lots of transformations are not linear, mainly for us, that's translations. We don't use 3x3s for 3D space, we'll use a 4x4. And essentially the last row and column are reserved for things that are affine. Okay, or if we're doing a 2D transformation, we would use a 3x3 so that we can do affine transformations. Even if the one we're not doing, the one we're doing is not affine. If it was linear, we could use a 3x3 to do a 3D transformation. But since we're going to kind of be able to pair them together and do a translation, then a rotation, then a reflection, I need them kind of all be the same size. So we use a 4x4 so that we can include affine transformations with our other ones. Okay, another really big difference is lots of computer graphics use row vectors rather than column vectors, which probably in terms of the way you input typing, a row is probably a lot easier to do, which is probably why they do that. But the way we generally have done the majority of what we've been doing, we've done like A times a column vector. Okay, and so whatever A does, we'd have multiplied it by a column and it would do it to X there. In our graphic applications, we're going to be multiplying from the left by a row. So it does change the matrix that we use to do that transformation a little bit. But we're going to do row vectors times our kind of transformation matrices here. And because our transformation for 3x3s, we'll be using 4x4 matrices. We need 4 elements. Oops. We need 4 elements in Y, but it's 3x3. So all we do is we kind of tack on a 1 right here. And then when you're doing your computer program, you'd have it ignore the 1 if you're graphing this information or having it show up on the screen somehow. You'd have it ignore that 1, but the 1 is kind of just a placeholder for you to be able to do this multiplication. It'll also, again, cause the translations to work. So whenever we input a coordinate, we would use XY1 or XYZ1 so that we could kind of use a one-dimensional higher set of matrices. All right, first one we're going to look at is translation. Translations are not linear, so again, for our purposes, this is the main reason we have to look at 3-dimensional transformations with a 4x4 matrix or 2-dimensional transformations with a 3x3 matrix. A translation is a super easy transformation to do, right? You're just adding. So if I want to move along a vector, I would just take a point. And all I would do is add the components of vector v0, and I would get my new point over here. With matrices, we could take a bunch of points. And instead of adding every time, we just multiply all the points at once by that same translation matrix, and it will move all the points at once. And so what if you had an original shape made of a bunch of points, it would move the entire shape and all of its points along that same vector. So yeah, if we wanted to do them individually, you could just add. But two reasons we do matrices: one, we can do it to thousands or millions of points at once. Also, we can then again pair these up to get more complex things than just a translation. We could get a transformation that does a translation, a rotation, and a reflection all at once. So that's the benefit of a matrix. That's why we do some of these really simple things, even with matrices, is once we get these together, we can make complex transformations using those. So this is a translation matrix in 3D. It's the identity matrix. But that last row that I said is kind of reserved for affine transformations, that's where you put in the vector that you're translating across or along, I guess. Okay, in 2D, you would just have your X naught, Y naught down there. So if we wanted to move a bunch of points along the same vector, you would just put those points into an m/4 and multiply it by this 4/4, and we get another m/4 where everything's been translated. So here I put in x1, y1, z1, x2, y2, z2. These are basically your coordinates here. And notice when I multiply rows times columns, I'll have x1 plus 0 plus 0 plus x naught, and then 0 plus y1 plus 0 plus y naught, and then 0 plus 0 plus z naught, z1 plus z naught, and then 0 plus 0 plus 1. And then you'd have x2 plus x naught, and y2 plus y naught, and z2 plus z naught, and then 1. And so you'd see you'd get on the other side, what would output is every single one of those coordinates with the vector having been added to. Again, very simple operation. Your goal would be that you could then pair this up and make more complex movements by putting these together with other things. Multiply the matrices together and you'll get a new matrix that does multiple transformations. Okay, so this is your translation matrix. This is the one we'll use for either 2D or 3D here. Okay, for scaling, again, scaling itself is a very simple operation. If we want to scale everything by the same scalar factor, we just multiply. Okay, multiply by the scalar. We can use matrices for several reasons. One, we don't have to multiply every dimension by the same scalar if we use matrices. We could kind of cause it to stretch in different directions. The other thing is, again, we could interact with other types of transformations. And you could do it to large amounts of points at once. That's why we use a matrix instead of just multiplying by a scalar. So if we want to change dimensions, and we reserve the ability to do it different dimensions in different directions. So C1, C2, C3, we'll just multiply the x's by C1, the y's by C2, the z's by C3. If you make them all the same, you'll get a proportional resizing. So like here, this is a two-dimensional matrix that would rescale an image by 90%. Okay, shrink it 90% its original size. So again, our copy machines that we have the ability to do that so that you can keep a margin around a page if I'm photocopying something that goes edge to edge. It'll kind of shrink it to keep a margin around the page 90% in every direction. Okay, so if we wanted to take a 3D image and do 30% in the X direction, 60% in the Y, and then twice as large in the Z, we would just take basically the identity and we would change the ones that are on the main diagonal. So we'd have a 0.3, a 0.6, a 2, and then the last one would just stay a 1. Scaling is linear, so that last row will just be 0, 0, 1. Okay, and this would cause, you get a similar image. You'd still be able to see what the original looked like, but it'd be kind of stretched out. It wouldn't have scaled proportionally. And what we do is we put points on this side. And then we multiply and we get our new points out on this side, okay, in a matrix. Okay, and they'd all have been scaled and stretched out, and you'd have your, whatever your original shape was, you'd have the new shape that was similar shape, just kind of stretched and scaled in different directions. So our general form of our scaling matrix, just the identity matrix, but along the main diagonal, you'd put your scale factors for the X, the Y, and if there's a Z, the Z. And again, make the C's all the same. It'll scale proportionally. Make the C's all different. It would stretch it in different directions differently. Okay, so say we wanted to scale a triangle with vertices 1, 1, 0, 1, 0, 3, and 2, 2, 0 by 300%. We would put in those coordinates 1, 1, 0, and then we'd add a 1 on this side. 1, 0, 3 with a 1, and then 2, 2, 0 with a 1. We'd multiply by a matrix with 3s on the main diagonal, except for the last number would just be a 1. Okay, and again, what we would get out of that is exactly what you would think. It's just taking every coordinate and multiplying by 3. This is just a way to take thousands of coordinates or millions of coordinates or billions of coordinates. Do that. It allows us to scale in different factors in different directions. It also allows us to pair this up with other types of transformations. That's why we use a matrix, even though it'd be easy to just multiply and get 3, 3, 0, or 3, 0, 9, or 6, 6, 0. Is we can then kind of pair these together, get more complex things. Okay, with scaling, I would take my original triangle, and what would happen when you scale is it's as if you drew lines from the origin through those points. And it would move out along those points 3 times the distance in this case, because I did a scale factor of 3. So it would move 3 times farther here, 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 and you'd get the same shape 3 times as large. It's gonna have moved away from the origin as well when we scale. So keep that in mind if you were doing computer graphics and you wanted it to maybe grow from a vertex and give the visual idea that it's kind of growing out from a vertex, you would want to pair this up with maybe like a translation vector that would take you back, so that when I did it, it would grow from there instead of grow out from the origin. Or if I wanted it to look like it was growing from the center in all directions, I'd find the center of this triangle and the center of this one, and I'd find the vector that would take the center of one to the center of the other. Then it would appear as though that scaling was happening from the center of the triangle instead of from the center, from the origin itself. So just keep that in mind, that if you do a scale factor and you're doing some sort of graphics, it's going to look like it's kind of coming out from the origin and getting larger that way. Factors greater than 1 cause growing. Factors between 0 and 1 will cause it to shrink. Negative factors will just cause it to go the other way, and it will change the orientation. But it would do the same, like a -2 would make it twice as large. It would go back into the distance this way. and it would flip it upside down. Okay, rotation. We're really gonna do mostly 2D rotations because 3D gets a little bit complex when trying to picture what's happening. But typically in 2D, we would rotate about the origin counterclockwise, just like we have since you guys started doing like unit circle, everything's kind of counterclockwise. So this is a matrix that would cause your 2D rotation. We've seen it before. 3D, we don't really talk about rotating counterclockwise around the origin because in 3 dimensions, that's not very descriptive in terms of what that would really mean. In 3D, we typically talk about rotating around an axis. So you might rotate around the x-axis or around the y-axis or around the z-axis, around other axes. You can look those up, and those are your your typical 3, or the x, y, and the z. They look very similar to this one. You can even rotate around other lines. But typically in 3D, we have a lot more choices on where we would rotate. So we're going to stick with 2D just again to keep it kind of simple. It's not a very huge leap to look up some 3D ones. We were curious how that would work. We don't really do any memorizing anyways. So yeah, you can look those up if you really wanted to, but we'll mostly do 2D. So basically I could take like points. I could do a rotation. I could scale. And I could translate. If you multiply these together, you'll get one matrix that rotates, then scales, then translates. And so that's how you get more complex changes, is you take these really simple things and think, how would I get from here to here via some simple transformations, put them together, literally multiply their matrices together, and you'll get a transformation that does that thing. It gets you from one place to the other. Order matters. It's like this one would literally rotate. Okay, whatever's next to where you're putting the points is going to happen first. Then it would scale, then it would translate. And often if you do it in a different order, you will not get the same location that you're trying to do. Okay, our standard rotation matrix rotates around the origin. If you want to rotate around another point, we literally could just shift everything over to where that point is the origin, rotate, then shift back. So this is an example of what I mean by you could pair or like group these up together. Is, you know, we don't always want our object just spinning around in the middle of the page. Maybe we want it to rotate around something else like the point 2, 3. Well, what I do is I literally take all my points, shift them left 2, down 3, okay, which is what this matrix here does. It would take all my points, I would put the points on this side. It would shift them all left 2, down 3, which would mean now when I do my rotation, what was the point 2, 3 is now at the origin. So I could then do my normal rotation and then shift everything right 2 and up 3 to kind of put it all back where it was. So I would do my rotation, then put it back. If I multiply these together, this is a rotation matrix around the point 2, 3. All I'd have to do is change those numbers, the 2 and the 3, and you could rotate around any point you want. Multiply this together, that is one single matrix that visually what you'd see is your thing rotating around the point 2, 3, as opposed to rotating around the origin. You wouldn't see the 3 individual things happen, right? Yes, technically what's happening is everything's moving to where that point is the origin, it's doing your rotation, and then it's moving back. This visually would just look like you're rotating around the point 2, 3. If I were to kind of make this into a matrix and you do the multiplication. But if you did them individually, yes, you'd see it kind of move over, you'd rotate, and then you'd move back to the same place. Okay, you could also think of rotations or reflections the same way. If you learn how to reflect over the x-axis and the y-axis, you could rotate the x-axis to be parallel to the line you're trying to reflect across, reflect, and then just kind of rotate everything back. And you could think about getting your different rotational matrices, reflection matrices, reflect across the line y equals x or y equals 2x, just kind of like move everything to where it would be, do it, and then move it back. And then that would give you matrices that do more complex things. Okay, the last one we're not even going to go into because we've already done it. And so you can look back at your notes because we did projections. We did projections using matrices. And this would be the exact same thing. Okay? And typically this is used to take something like a 3D object and get a 2D image in a plane. So think like getting a shadow or something, or a reflection in a mirror or whatever of your object. So if I have this object out in space, you may want for graphics purposes to kind of get its projection into the XY plane. Okay, or you get its projection into the XZ plane or whatever. You're just getting kind of its shadow in that plane or its reflection in that plane, what it would look like if there was a mirror there or something. That's the image that you'd be getting over there. So typically graphics wise, this is where you'd see projections. Your basic ones would be projecting in the XY plane, the YZ plane, the XZ plane, which are easy projections to do. And again, you could make those more complex by doing reflections or rotations to kind of get where you want to be. You could rotate the object, do the XY rotation, XY projection, and then rotate the object back. And then you'd get it in a different place or whatever. So this gets more complex by just kind of putting these things together to get, if I wanted a reflection that was in a different plane, you could rotate everything to where that XY plane was in the same location as that plane, do the projection, and then kind of rotate everything back or whatever. Okay. Again, you guys have a problem set due tomorrow from last week's notes. We have one due Friday, which is also a MATLAB day, our last MATLAB. Monday, your MATLAB from last Friday is due next Monday. So if you haven't done that or if you weren't here, that's due next Monday. And then next Tuesday, your last problem set is due. And then next Wednesday, you have your last test. So lots of lasts in the next couple weeks here. If you guys need anything, let me know. If you do not, you guys have a good rest of your day, and I'll see you guys tomorrow.